Hello, this is Melissa Griffin. I'm going to present to you the particle swarm optimization algorithm. It's a description of the particle swarm optimization algorithm, also known as the PSO, and a demonstration of an application I developed to give a demonstration of the PSO. PSO was created in 1995 by Kennedy and Eberhardt. They were trying to simulate the flocking and schooling patterns of birds and fish, like how it is in Finding Nemo with the fish doing their charades. They basically wanted to model the simple behaviors of individuals and their local environment and the neighboring individuals in order to obtain more complex behaviors that can be used to solve more complex problems. Basically, they saw how they could study the movements of the individuals in the community and how the community itself was able to find solutions to problems, and this was mainly applicable to optimization problems. A good analogy that is used for the PSO algorithms is the searching for treasure analogy. Imagine you and a group of friends all know that there's a treasure in a field, and you know the general area where the treasure is at. You also all have walkie-talkies, and at any point in time, you know who is the closest to the treasure. So you set out through the field, and you all have metal detectors, and as you keep getting closer to the treasure, your metal detector goes off, and you keep telling your friends where you're at, and they tell you, and you eventually all are moving towards the treasure at the same time, and then converging on that point. The treasure for a PSO is generally a maximum or a minimum, where the particles are going to move towards the maximum of a function or the minimum, depending on what you are looking for. So this is an example of how the particles would actually be looking for the solution of a function. This is the Bohachevsky 3 function. You can see the equation for it right here. If you were to send out particles looking for a maximum or a minimum, they would, for a maximum, be looking at these red areas here in the four corners. And the minimum, they'd be looking down here in the blue. As you can imagine, if you have them looking for the maximum, you might end up with 4 separate piles of particles. They might get confused because the ones that start here would end up converging on this area, and the ones that start here converge here. And if you're looking for the minimum, it might be more likely for the particles to find the minimum as opposed to the maximum. So this is a flow chart that represents the general flow of the PSO algorithm. So what you're going to start with is initializing the particles. That's setting them up inside the grid, as far apart or as close apart as you want them. You're going to calculate the value of the function at each of those points that you initialize it at. And then you're going to check the particle's current best value. The current best value is the value that is closest to what you're looking for that particle has found so far. So let's assume we are looking for a maximum. The particle's current best value is going to be the largest value it has found at that point in time. Now for the first iteration, obviously, it's going to be the only value it has found. So if the new value is not better, you will do nothing. However, if they find a value that is better than their own personal best, we will replace it with that new value. The next thing you're going to do is check to see if any of the particles have a personal best that is better than global best. The global best is just the best value that any of the particles have found. After this, we will calculate each particle's new velocity and position, which I will explain how to calculate that later, but it's based on the particle's personal best and the global best. And then when we reach the number of iterations we want, we will end it. Now, the number of iterations is dependent on the user, however many iterations you want. But if you want the global minima or maxima to be found, it makes more sense to have more iterations because it's more likely that the particles will converge on what you are looking for. This is the velocity equation that I mentioned earlier. I'm going to tell you what all of the variables mean, then kind of show you how they go together. So omega is a inertial weight component. It basically gives the particles a real life mass characteristic. It basically keeps them from zooming too fast all over the graph. Then you have C1 and C2. These are just some arbitrary numbers. They are used to weight the personal best, which is this P of x, and the global best, which is G of x. Basically, if you want the particle to move towards its personal best more so than its global best, you would weight C1 as higher than C2. For my application, I wanted them to move towards them equally and take them into consideration equally, so I set them equal to each other. R1 and R2 are just random elements that help make the simulation seem more realistic, because you don't necessarily know how something is going to act, a particular particle. These I also set equal to each other, but they were still generated randomly. So you have your new velocity, that is just the old velocity multiplied by the inertial component, plus the amount it should move towards its personal best and the amount it should move towards the global best. And you calculate it for both x and y. Then to get your new position, you just take your old x component and add in the new velocity that you just calculated. And you do the same for y. Some common applications of the PSO algorithm. First and foremost, it is an optimization algorithm. It actually is competition for genetic algorithms. This is because it can basically do the same thing, can optimize stuff. And the reason it is better in a lot of cases is that it is easier to implement and it takes less parameters than genetic algorithms do. PSOs have been used in neural network design, route planning for unmanned aerial vehicles, photovoltaic systems, and they're implemented very frequently in control systems. And one step into that is a fuzzy control system. And fuzzy control systems have been used for anything from brakes in automobiles to position control and path planning in robotics. This is a demonstration of the particle swarm optimization application. The first function that we're going to look at is the Bohachevsky one, which is this one over here. And as you can see, all the particles are just laid out one by one. When I press start, they're going to start converging onto what should be the optimal value. For Bohachevsky, the optimal value is 0, and it's found at 0, 0. Bohachevsky generally does better than 74% convergence. Normally it's around 90. But as I talk about in my paper, with the random element being put into the velocity equation, it just kind of depends on how well it's going to converge. Next, we're going to do ESUM, which looks like this. ESUM's optimal xy coordinates are pi and pi. We're going to zoom in. As you can see, a lot of them did come onto there, but there's a lot that ended up being on the outside. The last one we're going to look at is Beal's, which is this one. Beal's also often has very good percent convergence. It's optimized at 0 with xy coordinates of 3 and 5, and 0.5. So as you can see, the way that a function looks topographically definitely affects how well it converges on something, onto the optimal value. So in conclusion, the PSO is a very versatile algorithm. It's been applied in many fields, and even if it has not directly been applied in a field, it's been applied through another thing, like through a fuzzy control system. My application actually implements the most basic version of PSO algorithms. There are many different ways that you can have the particles talk to each other. You can have them only talk to their closest neighbor instead of having global best, stuff like that. And studies are ongoing to improve particle swarm optimization algorithms to improve the convergence factor, especially for some of those functions that didn't seem like they converged very well because of the way they were topographically.